It's my pleasure to next welcome Dr. Jonathan Earthy, who is Principal Human Factors Coordinator for Lloyd's Register and a Professor too at Haugesund University. He's also Chair of the ISO TC 159 Ergonomics SC4 Human System Interaction. And Jonathan's going to introduce the ISO standard for human-centered design. Jonathan.
Thank you, John. As Richard Vine mentioned, there is an ISO standard for human-centered design. This presentation describes it in more detail. Human-centered design is defined as an approach to systems design and development that aims to make systems more usable by focusing on the use of the system and applying human factors and usability knowledge and techniques. Put simply, it is putting use and the user at the center of design. Human-centered design is also known as user-centered design. In practice, the terms are synonymous. The standard specifies principles for a human-centered approach to the design of systems, products, and services. These principles are firstly to fully understand who the users are, their background, their knowledge and expertise, the tasks they're doing and the tasks you want them to do, and the physical, social, and management environment that they're working in. Second principle is to involve users as appropriate throughout the design and development. Third principle is follow an iterative approach to development governed by a user-centered evaluation ideally involving users themselves. Fourth principle is to address the whole user experience with the system, product or service. That's not just its use, but also its introduction, its training, any support that's required and how maintenance will be done. Finally, to include the relevant skills and perspectives in the design team to make sure that all aspects of the design can be covered. Compliant design process includes 5 activities. The planning determines the effort and interdependencies of the technical activities. For a new arrangement, system or procedure, you normally understand the context of use, generate user requirements, and develop a solution that takes account of human strengths and limitations. This is evaluated to see if it meets the requirements. If not, then it's most likely the design needs some tweaking. But a user requirement may have been missed. For something that has been in use for some time, it's more likely that the context of use has changed. The next presentation provides an example of the maritime application of human-centered design. You will see all of the human-centered design activities applied to bridge systems as recommended in ISO Circulars 1512 and 1609. Although the example is about manufacturers designing usable information technology, the approach and activities are equally applicable to, for example, the designing of ships and operating procedures to reduce fatigue as described in IMO Circular 1598. Thank you for listening.
I'm pleased to introduce our next speaker, Dr. Kjetil Norby, who is a Professor in Interaction Design from the Oslo School of Architecture and Design. He is the manager of the Ocean Industries Concept, working to improve design of maritime workplaces, an open source design resource supporting human-centered design of ship's bridge workplaces. Kjetil will present recent work done in the EU-funded SEDNA research project. This work is oriented towards preparing the industry to safely implement new augmented reality technologies for safe navigation. However, the project is also an example of how human-centered design can be applied in maritime research and development.
Thank you, John. There is a tremendous risk in operating ships in Arctic conditions, and in our work we have focused on reducing this risk by applying new technologies and user-centered design processes. In particular, we have focused on using augmented reality technologies on ships' bridges. Through the project, we have developed user-friendly harmonized designs for safe Arctic navigation by appropriating emerging augmented reality technology to enhance situational awareness and decision support. First, we have developed a virtual demonstrator of a ship's bridge. This includes a physical ship's bridge and an example of harmonized user interface design. Second, we have developed a series of augmented reality demonstrations of applications supporting safe Arctic navigation and operation, both in AR and simulated in virtual reality. Third, we have developed an interaction architecture supporting design of new AR systems. And finally, we have tested concepts through 3 scenarios realized in a VR demonstration. Our project deals with head-mounted augmented reality systems that allows us to freely position information to navigators anywhere in the world. AR has been around for many years, and it has been several research projects experimenting with the technology in the maritime domain. However, in our state-of-the-art review, we found that AR is still in very early development in the maritime sector, and there is no standards or guidelines for design of maritime AR user interfaces. This is a problem since badly designed AR can in itself be a safety issue in maritime operations, since AR may directly interfere with the user's outlook and attention. Our approach to AR differs from the current state-of-the-art in that we develop user interface frameworks supporting design of new AR systems. Also, we see AR as a platform for multiple systems used at the same time together with existing workstations, instead of addressing it as a single application system. We believe this better represents the structure of current ship bridges that are made up of a large number of individual systems. Therefore, our core concept in SEDNA has been to develop a framework for maritime AR design that support development of maritime AR applications for Arctic operations. And in order to do so, we have made a wide range of AR concepts and used them to develop a framework that describes how AR application can be designed, both individually and together as a larger system, in order to realize safer maritime operations. We have developed these frameworks through an iterative user-centered design process, where we have combined extensive field studies in the Arctic with virtual reality simulations on land. And here is a short video presenting more about how we have worked throughout the project.
There are many design systems for screen-based interfaces, such as the Open Bridge design system for ship bridges. But if you want to design for AR, you have to start from scratch. A ship bridge is a demanding environment to design for. In addition, there is a lack of good examples, guidelines, and frameworks for how AR should be used in such environments. In this video, you will see an example of how researchers at the Ocean Industries Concept Lab develop guidelines for using augmented reality on ships. In the SEDNA research project, we have applied a human-centered approach to develop and evaluate a proposal for using AR on ship bridges. Through several field studies, we learned about real conditions and user needs. This included everything from observations and interviews in context to various forms of workshops and co-design activities. Next, we mapped the bridge layout to discover how people move during different scenarios. The mapping helped us see when and where AR could be integrated. In addition, eye-tracking equipment documented how the navigator's attention constantly shifts between the instruments inside and the environment outside. This pointed to the possibility of using AR to move instrument information out closer to the ocean. Paper sketches allowed us to quickly explore a range of different ideas and solutions for presenting information outside. We photographed the sketches and brought them into the HoloLens headset to get an impression of how the interfaces would appear in AR. As the concepts became more defined, we created more realistic prototypes by connecting interface components to a digital simulator. Users provided invaluable feedback and were highly positive regarding the development of augmented reality. Back on land, we collaborated with domain experts and research partners to further develop the scenarios and AR concepts. For evaluating the potential of AR, researchers at Chalmers University of Technology reenacted 3 critical scenarios in a traditional bridge simulator. By recreating those scenarios in VR, we could seamlessly integrate the AR concepts. We used the Unity game engine, which allowed us to create highly realistic environments. Finally, once we have added various AR features to the scenarios, we could easily test the solutions with navigators. Since the VR scene can be exported as an application, it can easily be distributed digitally, allowing people in other locations to experience the new AR solutions.
The video shows some of the concepts we have been testing in the VR simulators at Chalmers. In our work, we envision AR as coexisting with all other systems on a ship's bridge, and because of this, it was important for us to make sure the user interface philosophy we applied to AR was compatible with the design of the rest of the ship's bridge. To achieve this, we integrated the OpenBridge design system in our approach. OpenBridge is an open source design system for maritime workplaces that are developed at the AHO. OpenBridge includes tools that allows for consistent design across all screens in a ship's bridge. By using concepts from Ship OpenBridge, we made an AR system design that delivers a consistent user experience across all OpenBridge compatible systems. OpenBridge were not adapted to AR or for workplaces in the Arctic before we started this project, and the SEDNA work therefore has been extending OpenBridge in two ways. First, it has delivered cases that show how OpenBridge can be adapted to AR, and these cases will be important in extending the public guideline into AR. Second, in order to better facilitate Arctic context, we have extended OpenBridge with an ice palette with extra high contrast meant to support use in bright light ice conditions. The palette is now part of the OpenBridge system. Here are some examples of palette trials we did in the Arctic together with human factor experts from University College of Southeast Norway. Throughout the project, we have brought with us AR equipment and used it to test the hardware and demonstrate AR concepts to end users in the field. Our first field trials used static demos, and later we included dynamic data from a simulator we brought with us onto the ships. In the end of the project, we were able to connect AR concepts to real ships. In the latter case, we collaborated closely with Ulstein Blue Control to establish a real-time connection to a ship in operation through their cloud software. Due to Corona, we were not able to travel to the ship and test it in real life. However, we plan to do testing of the software in new projects following SEDNA as soon as it is possible. The new design proposal was implemented in a virtual reality ship simulator we developed in the lab. The VR simulator combined our workplace design, user interfaces, and concepts from our AR trials into a realistic scenario realized in a game engine. The VR system allowed users to move freely in the virtual bridge and experience the ship in Arctic operations. Following is a video showcasing some of the concepts that we simulated in the VR system.
Augmented reality, also known as AR, is proving to be a promising technology. But can AR make it safer to navigate large ships? Or will the AR information actually be useful for the navigators? Well, let's find out. We will show you a range of examples of how we believe AR can be used on ships in the future. This is the result of several years of design research, including field studies, prototyping, and testing. We have recreated several scenarios in virtual reality to explore and demonstrate how AR could be used by navigators. Let's take a look at an accident scenario that happened in 2012. The cargo ship Vega Sagittarius departed from the port of Nuuk on the west coast of Greenland. Icebergs appeared ahead, so the vessel had to change its course. The navigators lost awareness of their surroundings, and as a result, the vessel ran aground on an underwater rock. Would this have happened if the navigators had AR headsets? Imagine you enter the bridge of the Vega Sagittarius. As you enter the workplace, an AR panel appears and adapts to your position on the bridge. In the AR panel, you see the most important information you need. As a result, you don't have to shift your attention between the environment outside and the screens inside. You approach some icebergs. This system identifies the objects outside and provides relevant status information. Small symbols above the horizon indicate your current course and heading, providing subtle feedback when the ship turns. As you approach shallow water, no-go zones are indicated on the ocean surface. Such overlays make it easier to understand how map-based information connects to the real world. Finally, the system informs you that you are approaching an underwater rock. In collaboration with Chalmers University of Technology, we have tested these AR concepts with several navigators. More trials are necessary, but the results so far indicate that these features could help prevent such accidents. Let's look at other examples of how AR can be used on the bridge. In this scenario, you enter the bridge of a small cruise ship approaching a large field of ice in Antarctica. On a large virtual AR screen, an ice forecast is presented to inform you about the conditions ahead. You can draw points on the ocean surface to discuss with your colleagues which route to take through the ice. The points are presented both outside and on the map. A grid and the radar image is overlaid on top of the ocean, helping you identify where you are in relation to large amounts of ice. As it becomes darker, you turn on searchlights, which you control simply by pointing where you want the light to go. To look at the conditions further away, you can use a night vision zoom camera and see the video feed next to the captured area. In the last scenario, you are on an icebreaker that is about to rescue a vessel stuck in ice, before escorting 2 vessels in a convoy. When you look at the ship you are approaching, information about distance and your closest point of approach is presented above the ship. You find the same information in the vessel list in the AR panel. There is another vessel behind you, waiting for the convoy to begin. A vector line on the ocean surface indicates where you will be in 2, 4, and 6 minutes if you keep your current speed and heading. Walking to the aft bridge, you can see the ships are lined up behind you. The Icebreaker Assistance app indicates the relative speed and distance between each of the 3 vessels. Back at the workstation, the Icebreaker Assistance app is also a part of the AR panel. This makes it easy to monitor the speed and distances between all the vessels. We use the examples you have seen to create components and rules for how AR applications on ships should work.
The application concepts developed in SEDNA has been used to evolve a user interface architecture describing how maritime applications should be designed in order to support maritime operations in a multi-system ship's bridge environment. The architecture comprises of 3 main elements. First is the AR application components. These are information elements that define different formats for how information are displayed in AR. Each of these components facilitate different information or application types. For instance, some application needs to be accessed in their entirety, while others need only smaller information elements or need annotation related to points, areas, or volumes in the world. Second is the information areas. They describe how AR components are organized in the physical world. And third is the AR zones. They define the way the organization of AR components adapts to the user's position in the real world. Throughout the entire SEDNA project, we have continuously presented ongoing results through industry meeting places in addition to academic channels. This dissemination has been important to make our work relevant not only for end users, but also for equipment manufacturers and the industry at large. We have also shared our results with over 350 companies worldwide by taking advantage of the OpenBridge network. The result from the SEDNA project is now integrated into new and ongoing research project at AO, and most notably, we were awarded 1.4 million euro in December by the Norwegian Research Council to continue the work. The project started in May 2021 and will extend the SEDNA AR framework into advanced maritime operations. The project will be open sourced and disseminated through the OpenBridge consortium. The project is led by AO and is a cross-industry collaboration between Kongsberg Maritime, Equinor, Technip FMC, Microsoft, Ulstein, Vard, Rev Ocean, the Norwegian Coastal Administration, and the Norwegian Maritime Authority. Thank you.